Welcome to part 2 of lecture 2 in chapter 13. And we're going to look at the stereochemistry of radical substitution and radical addition reactions. So let's go to the first real slide. We're going to look at this radical substitution reaction with an alkene. Actually with an alkane. Sorry about that. Now notice in this reaction that the reactant does not have an asymmetric carbon. However, after a radical substitution reaction, a product is formed that has an asymmetric carbon right there. A racemic mixture results because of R and S enantiomers that are formed. Here's the structure, and then it's shown here the stereochemistry, and that we do have a pair of enantiomers. Up here, bromine is substituting for a secondary hydrogen, as we have seen before, resulting in a racemic mixture of R and S enantiomers. Okay, let's take a look at this one, this slide. Here's the stereochemistry of radical addition to an alkene again. Stereochemistry of the products of the addition of hydrogen bromide to 2-methyl-1-butene in the presence of peroxide yields 1-bromo-2-methylbutane. Now, the stereochemistry shows that we get a pair of enantiomers being formed, as you can see. Both the radical substitution of an alkane and the radical addition to an alkene form a racemic mixture because both reactions form a radical intermediate. The radical intermediate in the substitution reaction is formed when bromine radical removes a hydrogen from the reactant. The radical intermediate in the addition reaction is formed when the bromine radical adds to one of the sp2 carbons of the double bond. So again, we can see hydrogen bromide adding to the alkene, showing the peroxide effect. That is, it's anti-Markovnikov. And as a result, we get a racemic mixture of R and S enantiomers, as shown on the slide. So in the case of radical substitution with an alkane, why are both enantiomers formed? As you can see on this slide, in the first propagation step, the bromine radical removes a hydrogen atom from the alkane, creating a radical intermediate. The carbon with the unpaired electron is sp2 hybridized, so the three atoms to which it is bonded lie in a plane. In the second propagation step, the incoming bromine has equal access to both sides of the plane, this way or this way. So both R and S enantiomers are formed. The same amounts of R and S are produced. You might want to note, it is because of the formation of a radical intermediate and its reaction that causes the configuration of the products to occur. So the same thing happens in radical substitution as shown on this slide, and radical addition, which will be shown on the next slide. In the case of radical addition with an alkene, you can see the situation. A similar radical intermediate forms. The radical can react with hydrogen on either side. There's hydrogen going on either side. So the stereochemical outcome of a radical substitution reaction is identical to the stereochemical outcome of a radical addition reaction, because both reactions form a radical intermediate, and it is the reaction of the intermediate that determines the configuration of the product that results. Here is a radical substitution reaction of an alkane. We have 2-phenylbutane. This is an asymmetric carbon right there. A hydrogen bonded to an asymmetric center is substituted by a halogen. As you can see, progressing over to the formation of 2-bromo, 2-phenylbutane. 2-bromo, 2-phenylbutane, a pair of enantiomers. Okay, so we have formed a pair of enantiomers. Identical amounts of R and S enantiomers are obtained when the hydrogen bonded to the asymmetric center is substituted by a halogen, as I said. Breaking the bond to the asymmetric center destroys the configuration at the asymmetric center and forms a planar radical intermediate. The incoming halogen has equal access to both sides of the plane, so same amounts of the two enantiomers are obtained in this reaction. Let's take a look at this simple problem here, relatively simple. How many isomers are formed in the radical addition of HBr to 1-methylcyclohexene? Let's pause. Okay. Now you can see this is a methyl group. There's one proton on here. We have the presence of peroxide. So the bromine is going to be electrophilic going to the sp2 carbon with the most protons. Since that one doesn't have any, that's got one. We're going to put the bromine right there. This is an asymmetric center, and this is an asymmetric center. Therefore, with two asymmetric centers will allow 4 isomers, 2 raised to the second power. So D turns out to be the correct answer. Moving right along, radical substitution of benzoic and allylic hydrogens. So let's discuss a few more remaining kind of miscellaneous topics involving radicals. And that is radical substitution of benzoic and allylic hydrogens. This is an allylic radical. Notice that is an allylic carbon because it's bonded to an sp2 carbon right there. An allylic radical has an unpaired electron on the allylic carbon due to the removal of a hydrogen with one of its shared electrons. Just like an allylic cation, it has 2 contributing resonance structures due to the presence of a double bond. So there they are. Adds a lot of stability. This is also an allylic carbon. This is an allylic carbon. In both of these resonance contributors, that is the carbon adjacent to an sp2 carbon. This is a benzoic radical. Notice the benzoic carbon adjacent to an sp2 carbon. And again, this is a benzoic carbon over here. A benzoic radical has an unpaired electron on the benzoic carbon. Like a benzoic cation, it has 5 contributing resonance structures, which is very stabilizing. So we're still talking about radical substitution of benzoic and allylic hydrogens. And you can see the relative stabilities of radicals. Of these radicals, you can see here's benzyl radical, allyl radical way over on the left being most stable. And then we have tertiary, secondary, primary radicals, and then finally vinyl and methyl radicals being the least stable. Notice there's delocalization of electrons possible in these two way over on the left, making them very, very stable. So benzyl and allyl radicals are shown to be more stable than alkyl radicals. Again, this is because their unpaired electrons are delocalized. Remember, electron delocalization increases stability of a molecule, just in general. The more stable a radical, the faster it will be formed. So a hydrogen bonded to a benzoic carbon or an allylic carbon will be substituted in a halogenation reaction before other hydrogens. Okay. The more stable radical forms faster, of course, as we just said. Here are a couple of examples, or one example, and then there's a second on the next slide, of radical substitution of benzoic hydrogens and allylic hydrogens. This one here is a benzoic carbon right there, and where it's going to become a benzylic substituted product. The benzylic and allylic hydrogens, as we see on the next slide, are removed to form a radical intermediate that's not shown, and then X substitutes for the hydrogen. Let's see, there it is right there. We kind of jumped ahead. So notice there's a little bit of heat put in here. So since bromination is more regioselective than chlorination, as you may remember, the percent of substitution at the benzylic or allylic carbon is greater for bromination than for chlorination, as X can be chlorine or bromine, as you can see here. Okay, here's the case of the allylic hydrogen. This is the allylic hydrogen right over here. That's allylic carbon. Allylic substituted product results as another good example of radical substitution. Now, in radical substitution of the allylic hydrogen, because of the reactivity of allylic hydrogens, a milder bromating reagent can be used. And this is illustrating the use of NBS, N-bromosuccinimide. It has an advantage in that the double bond is spared by NBS. It will not add bromine to the sp2 carbons on this cyclic alkene. So as we can see from this slide, N-bromosuccinimide, NBS, is a milder brominating reagent. It allows a radical substitution reaction to be carried out, as you can see, without subjecting the reactant to a high concentration of molecular bromine that could add to the double bond. Cleavage of the nitrogen-bromine bond right here makes the bromine radical needed to initiate the radical reaction, resulting in what we need. Lighter heat and a radical initiator like peroxide are used to promote this reaction. Okay, now on the next slide, we have the reaction of cyclohexene with the bromide radical. This is another example of radical substitution of an allylic hydrogen. Notice, this is the allylic carbon, and we have now substituted radical substitution for the allylic hydrogen. The bromide radical abstracts a hydrogen from the allylic carbon, and the allylic radical then abstracts a bromide from the molecular bromine that's present, forming the product. Let's continue talking about brominating allylic radicals. This reaction is a source of molecular bromine. Notice Br2. This can be used to brominate the allylic radical as in the last slide. N-bromosuccinimide reacts with hydrogen bromide to form succinimide and bromine. The bromine is used in the bromination of an allylic radical, as we've seen on several of the previous slides. Here is a radical substitution of an allylic hydrogen. If a radical abstracts a hydrogen atom from an allylic carbon, the unpaired electron of the allylic radical is shared by two carbons. So the allylic radical has two resonance contributors. In this reaction here, only one substitution product is formed because the groups attached to the sp2 carbons are the same in both resonance contributors. So as a result, when bromine comes in, we get the same product, 3-bromopropene. The source of this bromine right here could have come from the N-bromosuccinimide reacting with HBr as in the previous slide. Okay. Unlike the previous slide, in this reaction, the groups attached to the two sp2 carbons of the allylic radical are not the same in both resonance contributors, as you can see. So two substitution products are formed, 1 and 2. In the above diagram, the bromines are left off of the two products. They should be drawn in. Let's see if we got the right structure.